Hello everyone. Today we will be talking about a very interesting subject called deep learning or deep neural network. Actually, this subject is like a very famous subject now, and many people are, utilizing deep neural network for diversity of applications. So, what actually we will start with is actually the theory of machine learning. And the reason is one would say, okay, now we are talking about image processing, so why we do machine learning? Actually, the basic idea of deep neural networks comes from the machine learning. So in order to understand how deep learning work and can be utilized to solve problems like object detection or image classification, we need to understand the source or the main idea where it comes from. So like the first part of this presentation, I will be talking about the theory of machine learning, the domain of applications for both machine learning and deep learning, and then the software tools so that you can utilize it. Of course, there is a very powerful, resources using MATLAB. So we will talk about this. So let's see the guidelines of the presentation. I will talk a little bit about motivation. Why do we need deep learning? Why, where, and what is the intuition of deep learning, where it comes from, why it's important, the type of jobs and type of applications. And then we'll talk about machine learning, what is machine learning, what is traditional machine learning, and how we moved from traditional machine learning to deep learning. Then I will talk a little bit about artificial neural network, which is something that definitely have been used successfully in solving variety of image classification problem. I mean, like neural network itself is used for classification. Remember, we talked about enhancement, segmentation, and then the last phase is recognition. So neural network can be utilized for recognition of images. And then we will go in the second part of the presentation, we will go more deeper in the deep neural network, understand the architecture, understand the component, understand every layer, how it works, and then we conclude by current research direction and open research direction. So in actually this statistics is from 2013, and the deep neural network came as one of the 10 breaking through technology. So as you can see here, it's deep neural network comes here as 1, 2, 3, 4, 5 as a fifth grade or fifth level as one of the 10 breaking technology. Actually, deep neural network was discovered in 2011 by some researcher from Canada, and then and some, of course, researcher from USA utilized the idea for more and more, and were able to expand it. So in USA, deep learning market, this is the statistics from 2014 to 2025. So the market of deep neural network is booming, is growing. As you can see here, from 2014, the amount of money is like about $98 million, and then it grows up. This is distributed between software, services, and hardware. And the job market actually is growing. See, so the job market indeed. So machine learning engineer was the first one, and data scientist and computer vision, and so this area became one of the top area for recruitment in United States. Growing use of deep learning at Google, and Google, of course, is one of the very big companies that use deep learning, and they have like an R&D, research and development center, where they do lots of research on application that related to image understanding, maps, natural language understanding, robotics research, speech, translation, and so on. So it's really deep neural network offer a wide domain of application that can be used and utilized. And one would say, I mean, maybe we answered it early. Why is that? Because actually the huge amount of data that we are utilizing today is unlimited, and there is a need for powerful tools that can really adapt or deal with all these data sets. So deep learning is the domain where it can handle all this large data set. So we said machine learning engineers earn an average salary of between $142,000 about $142,000 per year in 2019. So based on some analysis on open position on Indeed. So as you can see, this number is like a big number. So it's really a competitive AI job market. Now, if we look here again to answer the question of why or the motivation, as you can see here on the left, the x-axis represents the data and the y-axis represents the accuracy. So if we look at the curve, the green curve, it shows the traditional machine learning, how it grows. But with deep learning, we were able to break that limit and move up with huge amount of data. So there was some kind of saturation with traditional machine learning, but with deep learning, we were able to grow more and more. And here you can see this is a source of deep learning, number of search for deep learning from 2011 to 2017. As you can see, it is growing. I mean, like almost saturated. Deep learning today, okay, now would ask what is the achievements or advancements in deep learning. Deep learning, the area which is really very successful is computer vision. So in computer vision, there is a tremendous number of applications where people use deep learning for computer vision. Natural language processing is definitely a successful area. Now you can find many devices that can really immediately be able to communicate and translate languages and understand languages using deep learning. And of course, speech recognition is one of the very important and interesting area nowadays. Why we need deep learning? Again, as we said, this is a characteristic of world population by region, and this is the amount of people. And if we look here, this is global data sphere. This is the annual of global data sphere. So the data size is going over terabytes. So because of the huge amount of data with growing population, the data grows in all sectors. How much data is collected every minute of the day? For example, if you look here on Instagram, for example, there is 277,000 user posts in a minute of the day. And if you would like to look at let's look at the one on the right. So on YouTube, users upload 300 hours of new videos every minute. If we look at the Amazon, okay, so we have 4,300 unique visitors per minute, and we have 3.2 billion people are accessing the internet and looking for data or providing data per minute. That's really huge amount of data. In order to understand, in order to extract, in order to conclude, in order to analyze this data, we need really a very powerful computers, and along with it a very powerful tool that can work on this data. One type of data set, just if you'd like to go and check, it's called Seafarer 10 data set. This data set consists of huge amount of images for automobile, birds, cats, deer, dogs, frog, horses, ship, trucks. So huge amount of data. And this was one of the data set that people started to work with at the beginning to explore the advantage of deep neural networks. So if you have all these data set and you would like to build a learning model that can differentiate between each of these objects or target or class, then you might need to look at deep neural networks. So this data set that was used successfully with deep neural network had 50,000 training image and 10,000 testing image with 10 classes or categories. And the accuracy by human being for the detection of the difference between these objects or classes was 94%. But with deep neural network, it went up to 95.5%. So that's really a great one. Also, the MANIST data set, this data set is actually was used successfully for recognition of text or like handwritten numbers. Okay, so it contains about 60,000 training image and 10,000 testing image. One would say, what is training and testing? We will talk about it. But so the total number of images that's available was about 70,000 images. Okay, as you can see, handwriting is not really consistent in all cases, and really you would like to recognize it. And then if we go to a deeper or a much harder problem is the signature recognition. Okay, and you remember the idea of the plate recognition problem. So we try to recognize where is the numbers of the plate or where the plate located. Then we try to enhance the image. Then we try to segment every single character or number or digit, and then after that we start to do the recognition. So here in deep learning, the problem is much easier to be solved. So this is as we said, curve of data, and this is a better recognition. Now as you can see here, this is a traditional deep neural network, traditional machine learning. In the middle there is neural network, and up there is a deep neural network. Actually, deep neural network is an extension for the common neural network or traditional neural network, and we will see that difference. Convolution neural network application, actually, it's as I said, it's huge, and I think it's a good idea that you try to explore some of these problems by looking at some articles or some research articles, maybe some videos that talks about this problem. So I think YouTube can be like a good resource. Springer and Elsevier articles are also good resource. So handwriting generation, actually not only recognition, is how can we learn the way somebody is writing, and then we can generate text. Music generation, this is also a very promising area. I know some people from Germany are working on this topic, and also speech generation. So actually, one would say, wow, how I'm going to do handwriting recognition? How I'm going to do speech recognition? It's actually, remember when we talk about the idea of, when you segment an image, you try to extract some features from this image, and then save these features for future use or future recognition. That's the same idea. If I can extract some of the features in the handwriting, and some of the feature in the speech, like frequencies or something, I can, of course, generate, handwriting and speech. Convolution neural network specifically for computer vision task, because this is is very interesting subject, and we are focusing on it here. Is one of the very famous is image classification. How can you give the deep neural network database of image, and then the deep neural network or convolution neural network specifically can learn the different faces or the different classes or the different types of images, and then once you get a new image, it can say, oh, this image is belonging to class A or B or C. Another application is object detection. So here we have the Petriastin, and then you would like to recognize if there is somebody is working. The second stage is actually to know if this is a kid or an adult or or an animal or whatever. So this is object detection is one of the area. And by the way, the MATLAB toolbox is having a very powerful computer vision toolbox that allow you actually to recognize objects from videos. So that's very interesting. Face detection and verification. So detecting faces in videos or images is like focusing on the images itself, then by detecting it, then verifying, then recognizing it. So this is also a two-stage process that deep learning can be used for. Pose estimation, like when in games like in karate or judo or all these kinds. So maybe you can recognize, detect, and know if this movement is correct or not correct. There is also a very nice application for arts, which is called neural style transfer. I like this one very much. So the neural style transfer actually depends on having a content image, and then you have a style image, and then you combine both of them to generate an output image like this. So actually you try to learn from this style image some features and then implement it or apply it on the content image. And there is very nice publications you can look at here on this link for style image. I like it really. So, and there is of course a principle for the combination, the way the style image is combined with the content image. And this is the paper. So in this paper there was this image on the left, top left, which is have A, and then you change the style based on another image to see how the outcome, it looks very interesting. One of the very important also application for deep learning is a self-driving car. You know, the Google self-driving car, and Amazon is also working on that. So in self-driving car, actually the system need actually to care about many things, like, you know, detecting pedestrians, detecting other cars, you know, checking traffic lights, traffic signs, and so on, and also keeping the speed and direction, and you know, so there is a whole lot of research in this area that is counting on deep learning. And this is another example of how for example the car system in this case can detect or recognize different objects in an image. Deep learning was also used successfully for some medical application like cancer diagnosis. And this is really a very promising area. Of course, we can do cancer detection using traditional image processing by, you know, segmenting CT scan or MRI images, and then after that we extract the features and so on. But deep learning can do that in a very fast and automatic way. So this is brain MRI. Okay, now if you would like to see how this process works, so you start by, you know, getting the images, and then put the images as normal images and tumor images. We call it training data, or you remember when I talked about the supervised learning. So supervised learning is one of the main characteristics or main theme for machine learning. So we have supervised learning, unsupervised learning, and reinforcement learning. So in supervised learning, we teach the system by providing examples. So here we have examples of normal image, examples of tumor image. You feed it to deep neural networks, and then you once you do the classification, then you can test the network by feeding it again with test images, and you can get the location of the tumor. So we always have two phases for learning. The one is called training phase, and the one is called testing phase. In the training phase, basically you build the model that understand the normal and the tumor. Then after that you test it with some data. That's why we always like keep set of images on the side that the network will not be, you know, haven't seen before, to test the performance of the network, or the deep neural network in this case. We always say that deep learning is taking over machine learning, but I always like to say that deep learning is a component of machine learning, or deep learning is a sector of machine learning. So these are different types of application where that machine learning was introduced to it, and now deep learning is taking over, like automatic translation, traffic prediction, image recognition, email spam filtering, text and speech recognition. So all these kind of applications are really was solved before using machine learning, and now deep learning is taking over. Let's watch this video.
As technology evolves and the world's population grows, so does the amount of data being generated. Collecting, sorting, and analyzing all of this data can be pretty time-consuming. However, that's starting to change with the emergence of something called machine learning. Machine learning is a type of computer science that allows computer programs to learn and improve all on their own. In the past, computers could only do what we programmed them to do. But with machine learning, they can behave like humans and gain knowledge based on their past experiences. This process can get pretty complicated, but here's how it works on a basic level. Let's say we want a program that can tell the difference between apples and bananas. First, we'll give it some labeled pictures of each. The program will then look for patterns in the fruits and start to remember them. It can then use these memories to look at unlabeled pictures of apples and bananas and determine which is which, all on its own. Believe it or not, you probably encounter machine learning on a daily basis. Social media sites use it to create your feed based on your preferences, and search engines use it to improve the accuracy of their search results. It's also being used on a larger scale. The medical industry is applying machine learning to things like predicting lifespans, organizing patient data, and even diagnosing certain diseases. As with many emerging technologies, there's a concern that machine learning may eliminate certain jobs. This will vary from industry to industry, but it does have the potential to get rid of or change a number of occupations, including drivers, bankers, and potentially even certain doctors. While it may have some negative effects, many believe that its positive applications will outweigh them.
Goodwill Community Foundation, creating opportunities for a better life.
So what we see from here is that we have data, and this data is labeled, and that's why we call it supervised learning, and we feed it to the learning model, and then the model will learn the difference between label A and label B, and then can generalize.
We know humans learn from their past experiences,
Okay?
and machines follow instructions given by humans.
Now this part is
But
actually
what
about
if humans can train the
this part
machines
is
to
actually about supervised and unsupervised learning to show you the difference between both of them. All right?
learn from their past experiences, and machines follow instructions given by humans? But what if humans can train the machines to learn from their past data and do what humans can do and much faster? Well, that's called machine learning. But it's a lot more than just learning. It's also about understanding and reasoning. So today, we will learn about the basics of machine learning. So that's Paul. He loves listening to new songs. He either likes them or dislikes them. Paul decides this on the basis of the song's tempo, genre, intensity, and the gender of voice. For simplicity, let's just use tempo and intensity for now. So here, tempo is on the x-axis, ranging from relaxed to fast, whereas intensity is on the y-axis, ranging from light to soaring. We see that Paul likes the song with fast tempo and soaring intensity, while he dislikes the song with relaxed tempo and light intensity. So now we know Paul's choices. Let's say Paul listens to a new song. Let's name it as Song A. Song A has fast tempo and a soaring intensity, so it lies somewhere here. Looking at the data, can you guess whether Paul will like the song or not? Correct. So Paul likes this song. By looking at Paul's past choices, we were able to classify the unknown song very easily, right? Let's say now Paul listens to a new song. Let's label it as Song B. So Song B lies somewhere here with medium tempo and medium intensity. Neither relaxed nor fast, neither light nor soaring. Now can you guess whether Paul likes it or not? Not able to guess whether Paul will like it or dislike it? Are the choices unclear? Correct. We could easily classify Song A. But when the choice became complicated, as in the case of Song B, yes, and that's where machine learning comes in. Let's see how. In the same example, for Song B, if you draw a circle around Song B, we see that there are 4 votes for like, whereas 1 vote for dislike. If we go for the majority votes, we can say that Paul will definitely like the song. That's all. This was a basic machine learning algorithm also.
By the way, this is the k-means. Remember the k-means clustering that we talked about in previous lecture? Okay, so in the k-means we try to see how each individual pixel is belonging to a domain. I think you should remember this, right?
It's called k-nearest neighbors. So this is just a small example in one of the many machine learning algorithms. Quite easy, right? Believe me, it is. But what happens when the choices become complicated, as in the case of song B? That's when machine learning comes in. It learns the data, builds the prediction model, and when the new data point comes in, it can easily predict for it. More the data, better the model, higher will be the accuracy. There are many ways in which the machine learns. It could be either supervised learning, unsupervised learning, or reinforcement learning. Let's first quickly understand supervised learning. Suppose your friend gives you 1 million coins of 3 different currencies, say 1 rupee, 1 euro and 1 dirham. Each coin has different weights. For example, a coin of 1 rupee weighs 3 grams, 1 euro weighs 7 grams and 1 dirham weighs 4 grams. Your model will predict the currency of the coin. Here, your weight becomes the feature of coins, while currency becomes their label. When you feed this data to the machine learning model, it learns which feature is associated with which label. For example, it will learn that if a coin is of 3 grams, it will be a 1 rupee coin. Let's give a new coin to the machine. On the basis of the weight of the new coin, your model will predict the currency. Hence, supervised learning uses labeled data to train the model. Here the machine knew the features of the object and also the labels associated with those features. On this note, let's move to unsupervised learning and see the difference. Suppose you have cricket dataset of various players with their respective scores and wickets taken. When we feed this dataset to the machine identifies the pattern of player performance. So it plots this data with the respective wickets on the x-axis while runs on the y-axis. While looking at the data, you will clearly see that there are 2 clusters. The one cluster are the players who scored high runs and took less wickets, while the other cluster is of the players who scored less runs but took many wickets. So here we interpret these 2 clusters as batsmen and bowlers. The important point to note here is that there were no labels of batsmen and bowlers. Hence, the learning with unlabeled data is unsupervised learning. So we saw supervised learning where the data was labeled and the unsupervised learning where the data was unlabeled. And then there is reinforcement learning, which is reward-based learning, or we can say that it works on the principle of feedback. Here, let's say you provide the system with an image of a dog and ask it to identify it. The system identifies it as a cat. So you give a negative feedback to the machine saying that it's a dog's image. The machine will learn from the feedback, and finally if it comes across any other image of a dog, it will be able to classify it correctly. That is reinforcement learning. To generalize machine learning model, let's see a flowchart. Input is given to a machine learning model, which then gives the output according to the algorithm applied. If it's right, we take the output as our final result. Else, we provide feedback to the training model and ask it to predict until it learns. I hope you've understood supervised and unsupervised learning. So let's have a quick quiz. You have to determine whether the given scenarios uses supervised or unsupervised learning. Simple, right? Scenario 1. Facebook recognizes your friend in a picture from an album of tagged photographs. Scenario 2. Netflix recommends new movies based on someone's past movie choices. Scenario 3. Analyzing bank data for suspicious transactions and flagging the fraud transactions. Think wisely and comment below your answers. Moving on, don't you sometimes wonder, how is machine learning possible in today's era? Well, that's because today we have humongous data available. Everybody is online, either making a transaction or just surfing the internet, and that's generating a huge amount of data every minute. And that data, my friend, is the key to analysis. Also, the memory handling capabilities of computers have vastly increased, which helps them to process such a huge amount of data at hand without any delay. And yes, computers now have great computational powers. So there are a lot of applications of machine learning out there. To name a few, machine learning is used in healthcare, where diagnostics are predicted for doctors' review. The sentiment analysis that the tech giants are doing on social media is another interesting application of machine learning. Fraud detection in the finance sector, and also to predict customer churn in the e-commerce sector. While booking a cab, you must have encountered surge pricing often, where it says the fare of your trip has been updated. Continue booking? Yes, please. I'm getting late for office. Well, that's an interesting machine learning model which is used by global taxi giant Uber and others, where they have differential pricing in real time based on demand, the number of cars available, bad weather, rush hour, etc. So they use the surge pricing model to ensure that those who need a cab can get one. Also, it uses predictive modeling to predict where the demand will be high, with the goal that drivers can take care of the demand and surge pricing can be minimized. Great! Hey Siri, can you remind me to book a cab at 6 p.m. today?
Okay, I'll remind you.
Thanks.
No problem.
Comment below some interesting everyday examples around you where machines are learning and doing amazing jobs. So that's all for machine learning basics today from my side. Keep watching this space for more interesting videos. Until then, happy learning.
So I prepared, added these two videos because really it's summarized in a few minutes. What do we mean by machine learning? What are the main stream for machine learning? Quickly, we have supervised learning, unsupervised learning, and reinforcement learning. Supervised learning work with examples or labeled data. Unsupervised learning work with unlabeled data as the k-means clustering. So the data is clustered based on the closeness or the how close the data to each other. And we talked about the k-means clustering before, how we start by certain centroid, and then we keep moving this centroid based on the data set. And then reinforcement learning is a way to learn by making mistakes or reward. Sometimes we call it like this. So if you make a mistake, so you learn from it. If you do something good, so you get a reward. So that's the way it works in the two cases. Okay, there are right now many books that really focus on machine learning and deep learning and reinforcement learning specifically, and this is really a huge resources for people who would like to start working with machine learning. Okay, I will stop at this moment so we can make the size of the video acceptable, and then we will continue. All right, welcome back. So as we discussed in the previous few slides, we had number of ways, or we talked about the motivation behind machine learning and behind deep learning, and actually maybe this slide is like a little bit difficult to understand, but I will try to summarize it little bit. So the motivation of deep architecture, what deep architecture actually, if you understand neural network, and this is what we're going to do in the next few slides, you will understand what we mean here. So the neural network actually itself consists of a set of layers, and the number of layers is more likely traditionally is like 2 or 3 layers maximum, 1, 2, 3 layers maximum. But with deep neural networks, the number of layers is really deep. It means it could be like more than this, could be like maybe 10, 20 more than this layers. So we say insufficient depth can hurt. That's what we say about traditional neural network, which is more likely, one of the famous technique is feed-forward neural network. So with shallow architecture, we say with shallow architecture, support vector machine or KNN or other techniques can require number of nodes in the graph, which is like very, very big. I mean, it might be, not easy to do the learning process. So many functions can be represented efficiently with a deep architecture that cannot be represented with shallow one. What we mean by shallow, it means like the original neural network, which has a few layers. Okay, and why we do that? Because the brain, which is our brain, is already having this deep architecture. We could have like 10 to the power 8 neurons in the brain. That's a huge number, and that's a way the human being can recognize or memorize the activity. Now let's go to the difference between deep learning and machine learning, because many people are confused when we talk about this. In the late 50s and 60s, the idea of artificial neural networks and expert system was booming, and the basic idea with expert system was like creating a set of rules that this rule can represent a knowledge or experience of an expert person, or about or knowledge or experience about certain event or certain environment, how it works, and then we try to imitate or simulate this kind of experience and match it with other experience. But in the late 70s and beginning of 80s, the machine learning techniques started to grow, and specifically, actually, the neural network was like in late 70s where the first perceptrons and feed-forward architecture was presented and was successful. Then after that, many trends came for research, like Hopfield network, radial basis function networks, and many others. And in the 2011, the idea of deep learning. So there is no really kind of like a line that separates between these algorithms or these trends one another. But you can say that the big umbrella is artificial neural networks. The umbrella inside it is machine learning, and the next umbrella is deep learning. So if we draw like a circle, so it's going to be like three circles, one after the other. Deep neural network is inside, machine learning is outside, and then artificial neural network is going to be the big circle. So the basic idea is as follows. I mean, like if we look here on the idea here, you have data set that's coming from different sources, could be image, could be text, could be anything. And traditional machine learning counts on extracting feature vector from this data. As we did in image processing, we try to enhance the image, segment the image, we try to inherit the edges in the images, and then select different, extract different objects. And then after we do that, we have some pixels that represents each object. So we go back, based on the location of this pixel, we go back to the original image, get some of the feature in this image. And as I mentioned before in one of the papers which was published, which I published with some colleagues about oil spill detection. So the places or the area where there was oil, we went over there, we selected some of the features based on the area, based on some, like we calculate the mean, the skewy, other features, many other features. And then we say, okay, if there is an oil, so it is characterized by this level of or values of the features. So that's the way we do it. And then we take these values and feed it to a neural network architecture that could be like artificial neural network. And then after that, we get new set of images or data, and then follow the same procedures, and then we apply it to this model that we already trained and learned in order to predict what should be the label for this data set. And that's the way we do traditional machine learning. This is what we call traditional machine learning. So machine learning depends on extracting features and building a learning model in order to recognize different objects if we talk about image, or predictive modeling if we talk about let's say weather forecasting or customer needs or anything like that. So when you say so traditional methods or traditional techniques work like this. This is a very nice example on object recognition based feature selection and extraction. So when you have an image, you capture the image, then you extract set of features that characterize this image, and this basically are points in the space. So these points in the space actually can characterize a face, and then you make a comparison between these features and other features stored in a database, and then you can make the match. So that's what we did. So when you get a grayscale image, we try to enhance it first, and then we try to extract the location of the face based on the the features. And then here you are masking outside the face using not a number, so we have more focused here, and then we divided it to a grid. Here this method depends on the grid of 9 times 9, and then you select features, and then you have a feature vector. This feature vector you can feed to a learning model like neural network. So that's the basic idea. If you have image, maybe you can extract some part of these images as features, and then you can recognize it. And this is actually the beginning of the idea of deep neural network. So yeah, that's again the big building block here is AI. The second building block is ML, machine learning, and then DL, which is deep neural network. So deep learning deep neural network is a subset of machine learning based on neural network that permit a machine to train itself to perform a specific task. All right? Okay. This is also a nice representation of how deep learning augment the structure of the model. This slide is very, very important. Now, we said that, let's say we have an input, kind of an image, we extracted feature, then we do classification based on a neural network, and then we say, okay, if this object is true or false, is yes or no, is a car or not a car, right? But in the deep neural network, actually you augmented the two phases, the feature extraction and classification, to one phase. So you take these two stages or two phases and augment it here in one phase, which is deep learning or CNN. Okay, that's a basic idea, or that's the main difference between these two techniques. Of course, feature selection here is implemented like in different ways. There could be tons of features that we can care about. And remember something, we usually try to get these features based on some sort of like equations, and this equation can be in some cases represents filters. Okay, when we try to extract, for example, lines or curves or thinning or anything, this is based on filters. So the filters is doing this task. So the feature extraction and classification in deep neural network is actually going to be built based on filters. Here is one more time the same characteristic before. This structure looks like something we call decision tree. So this one we call it decision tree. This is one way of classification. Classification, we have support vector machine, logistic regression, decision tree, and many other classification techniques. So what is the difference between machine learning and deep learning? Machine learning can give good result with a small data set. And in fact, deep learning needs a large data set. So you cannot really build a deep learning model with few images or few examples. Quick to train the model, the machine learning, but deep neural network is computationally expensive or intensive, so it takes some time. In some regular cases, you might take like maybe a few minutes up to a few days. So that's the case. Machine learning need to try different features and classifier to achieve best results. So that's what we mean by different classifiers and different features. As I said, the feature domain is huge. Sometimes in machine learning, what we do is we sometimes extract all possible features. Let's say we extract n features from certain image with different objects, and then after that we do some kind of feature selection to pick up the best feature that can represent an object, and then we take these features, feed it to a neural network or a classifier so that you can build the model. And of course, one classifier might not do the job. We might need to have number of classifiers to test it, or maybe we can have a hybrid classifier. Okay. Here, the nice thing about deep neural network, you do not really have to worry about what are the features or how they looks like or what are the best features. Actually, here, deep neural network learn the features by itself and then do the classification automatically. This is accurate, and this is accuracy is unlimited. So accuracy is very good. Now, these are some examples. I think this is some real world application. On here, on the top left here, this is a kind of a car that is learned or trained to in order to get to the end point without kind of hit the wall. So we have this green car, so it learns by doing mistakes or after different generation the performance is getting better and improved. See, so it gets better as a function of time until it reach the target goal. On the top right, we have a robot that really trained and learned in order to do some kind of movement, like jumping and so on. Okay, so this is Boston Dynamics. It's very nice. And on the right bottom here, you have like recognition of different types of. So you see the plate number, the type of the car, and so on. So you see the plate number, the parity, the color, the score. Oh, this is a car with a score of 0.8, like 80%, and so on. So this kind of application is very interesting for. So also there are some other definitions like data science. Some people talk about data science and mix the definitions. So this is also one of the definitions that you might want to know about. Like data science is a science that care about data collection, data cleaning, data subsetting or clustering, data manipulation, and data mining. So that's this slide might help you to recognize the difference between these techniques. Now, what is artificial neural networks? I will talk about what's artificial neural networks in few slides. I will try to summarize it. I'm not planning to go to deep details, but at least you can understand the basic concept. So when we go to deep neural network, things becomes much easier for you. So just to check. Okay, so everything is fine. Okay, so deep learning is usually implemented using a neural network architecture, and the term deep refers to the number of layers in the network. The more layers, the deeper the network. And it's simply why we call it deep, because it has more layers, because it goes deeper and deeper, and it can do some more function than the simple neural network. As I said, simple neural network here is basically working with maybe one layer or two layer or three layers maximum, and the kind of functions that exist in every neuron here might be a little different from the one that is in deep neural network. So, but again, you have input layer, the red one, you have the output layer, the blue one, and then you have the intermediate layer or hidden layer. That's what we call it in ULE 1. So here the same in deep neural network, you have input layer, output layer, and then lots of hidden layer. Okay. So if we go back to a shallow neural network, which is traditional neural networks, a neural network is essentially a weighted graph that takes an input and presents an output. And MLP, which stands for a multi-layer perceptron, is a widely spread neural network that is used for supervised learning, for example, image recognition. And the technique that we use for training the multi-layer perceptron is called back propagation learning algorithm. Okay. Now, how the neural network looks like, actually on the top here, this is the basic element for a neural network. The basic element consists of like a summation, that is a summation of the input values of x1, x2, and xn multiplied, each one is multiplied by w. So you have xi, wi from I equal 1 to n. That's basically the weight. And sometimes we add some bias term here like b, and the weight for the bias is 1. So sometimes we add here plus b, okay, as a bias. So bias is like the average value. And then once we get the output here, we pass this output, which is summation from I equal 1 to n. This is the same one as here. We pass it by a function. This function, most likely we call it sigmoid function. And this function actually creates some kind of nonlinearity. So it's not like a real linear function of the input, but it's nonlinear function in order to create nonlinearity. And there is a claim saying that a neural network can present any nonlinear system. Okay, so it can learn any nonlinear system, of course, if we have enough measurement. So this architecture on the bottom here is called the feed-forward neural network, or we call it multi-layer perceptron. So why multi-layer? Because we have more than one layer, and perceptron because a single computing element here is the perceptron. So this one is the same. So instead of having one unit like this, we have multiple units. One would say, one of the questions that always arises, so how many layer should I use in my application, and how many neurons in each layer I should use in my application. Actually, this question, there is no single answer for this. This depends mainly on the application. Of course, the more neuron in the hidden layer, the more complexity is the model will be, or you can say it in another word, the more ability of the neural network to represent complex model. Of course, when you have more than one layer, that will be better if you have a complex system. But of course, the number of input and number of output should be fixed, because I mean the number of input could be the number of pixels in an image, or a number of features. But I mean you cannot have more than this. And in the output, it could be like the class. If we have one class, then we have like yes or no, like 1 or 0. If we have more than one class, so we have 2 neurons or 3 neurons or n neurons. It depends on the number of classes that we have. Of course, even if we have class 1 or class 0, sometimes we represent it by 2 neurons. Like 1 neuron can produce 1 and 1 neuron can produce 0. It depends on the case. So if we look inside the perceptron, as you can see, the perceptron is actually have a sigmoid function. As you can see here on the right, it's 1 divided by 1 plus e to the power minus z. So this minus z, this z actually is what? This z actually is these values. As I said, you could have like a bias term, theta 0 or beta 0 or whatever you call it. I mean, it doesn't make a difference. Plus x transpose times theta. One would say, from where we got x transpose times theta, it's the input. This input x1, x2, x3, you put it in a vector. Okay, and as I said, 1 here is times theta 0, so this is 1 theta 0 here, plus summation xi times theta I, okay, which is here. So if we put this in a matrix format, so this will be a vector and theta will be a vector. So the result will be a value plus a value will give us g of a constant or a value. Then when you substitute here by different value of z, you will get the corresponding value for g, which is going to be in this case the output. So the output here is a value from minus, from 0 to 1, right? It could be from minus 1 to 1. I mean, it could be anything. I mean, based on the design of that circuit. So here it's from 0 to 1, as you can see. So when z is minus infinity, the value is 1. When z is infinity, is 0. When z is infinity, the value is 1. So that's the characteristics in this case. Now let's check some simple example here. If we have an image, let's say, which has number of pixels like this one, so you have number of pixels here, and we are presenting the number here, let's say number 2 with this number of pixels. So the pixels that really doesn't have any, part of the character or the number 2 is 0, and the one that has the character 2 is 1. Maybe you can present it like this. And you would like to have a machine that learn, so every time you get an input which is 2 or 3 or whatever, you get the output correctly. So if we look here, so we said we have a vector of input of 256 and the output is 10. Why the output is 10? So you have values from 0 to 9. That's the number of output or the classes that you can have. And 256 is because here you have an image which is, I think it's, 16 times 16? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 12, 13, 14, 15, 16, yeah, 16 times 16. So that's the vector of input. One of the output has the highest value, which represents a corresponding number. So the output here, when you have like, yes, it's 16. When you have the input vector is 256, yeah, that's nice. Okay. So we can have, so we convert all these values to one vector and so on. And then we feed these values to, and we would like to get the output. The output is from 0 to 10, right? Remember? So we have like 10 outputs. Each dimension represents the confidence of a digit. Like, let's say, when we have one of the output is high and the rest is low, so it means that this number is the correct number. Okay? So let's say we got the output like this, 0.1, 0.7, 0.2. So the corresponding value for the first node in the output is 1, and this is 2, and this is 0. So when you have a value which is high, like 0.7, so it means the output is 2. This is like the highest value at the output represents, so it means that the input was number 2. Of course, this value should be zeros, but it's because of some error or some learning performance. Okay, so that's the way it works. And this is writing digits. Okay, so we try to map 256 input to 10 output. In deep learning, the function f is represented by neural network. Let me show some little example here. Okay, so this is the operation that happens again at the neuron level. So you multiply the input by the weight, you get this equation plus the bias, which is multiplied here by 1, and then you take the sigmoid function, which is something like, as we saw, there is a number of sigmoid function. Actually, the one we saw was start from 0 and has a value, minimum value of 0 and maximum value of 1. So this is a weight, this is a bias, and this is the activation function. So if we build a multi-layer perceptron, not just a perceptron, so this is how it looks like. Number of layers, so we have the input layer, we have the output layer, and we have L layer inside. Okay, so this hidden layer. Of course, as I said, the complexity of the network or the neural network depends on the complexity of the problem. So if we have a simple problem, we shouldn't need that many layers as hidden layers. We shouldn't even need more neurons in the hidden layer than with complex problem. With deep neural network, this is like a kind of simulation. I'm not sure should we go through it in details, but just let's try part of it. So if we assume we have a weight like 1, minus 2, minus 1, and 1, one would say how we get this weight. Actually, with neural network, we start by random weights. Okay? And one would say, so any random weight? I would say yes, any random weight. But the thing is, neural network is actually the learning algorithm here, which is called backpropagation, is a kind of an algorithm that can start by local minimum. So if you imagine you have a search space, and this search space is full of hells and valleys, and your goal is actually to find out like the point of minimum or maximum on this surface. So if you imagine you start at a certain point in the space and you search in the neighborhood, if you are lucky enough, you will locate the global minimum. But if you are not, this means that you need to start one more time with a new random set of values, and then keep trying until you reach some good result that you feel satisfied with. And of course, there is no guarantee that this will happen, and that's why when we run neural network, we might need to run it many number of times and get many conversion curves of error until we reach some confidence that this is the best results. And that's why in the literature, I think in 1995, Professor Darwell Whitley at Colorado State University published his paper, which is called Neural Network and Genetic Algorithm, and it was basically using one of these evolutionary computation algorithm in order to tune the neural network weight and get some good results. So as you can see what happened here, so if you have 1 and minus 1, so what happened is, if you would like to do the calculation here at this point, so it means minus 1 times minus 2 will be 2, and 1 times 1 is 1, so 2 plus 1 is 3, and 1 times 1 is 1, so it's 4. So the output is 4. Now we take this 4, which will become 1 divided by 1 plus e to the power minus 4, and this will get us the output as 0.98, and so on. So that's the process that we follow for the next point. You see here we have, let me try it first. So you see here we have minus 1 times 1 is minus 1, and then minus 1 times 1 is minus 1, so minus 1 plus minus 1 will be minus 2, and plus 0, so it's minus 2. And then when we take this minus 2 and pass it here, so it's 1 divided by 1 plus e to the power minus 2, which is 2, and this will get us 0.12. So, and so on. You keep doing this until you do all the calculation, and at the output, then you start to look at this output and see if it matches your goal or not. If not, then you have to propagate back the error and recalculate the input. So that's the basic idea of neural network, which really can take considerable amount of time. But if we talk about how this algorithm works, so we said the feed-forward backpropagation neural network is a very successful network, and basically it works with the gradient. So backpropagation works like this. We randomly initiate the parameter of the system, and then we calculate the error at the output. And if the error is high, then we recalculate, calculate contributed to the error, and we update the weight of the network based on this error. So we have what we call as partial W, partial error, or partial E. Okay, so that's the idea of backpropagation learning algorithm. Here, actually, I have in this PowerPoint slides, I have more details about how this works, but I think we do not have the time, or that's not the goal of this presentation. Specifically, we need to move to deep learning, but I have all the analysis here. So if you follow up this kind of analysis, it will give you the output, and I'm showing you why we selected the sigmoid function as 1 divided by 1 plus e to the minus z. This function has many advantages when you differentiate it. So that's why we adopted this function. Okay. Now, there are actually, this softmax is one, but I mean, we can talk about it later on. But one of the things that people always, think about is the sigmoid function, how the sigmoid function should look like. So the sigmoid function in the hidden layer actually comes in the form of a tanh function, but the sigmoid function in the output layer, we most likely try to make it as a linear function. There are some other functions like softmax, and which we use more likely in deep neural networks. So it's something like the one that you can see, which is with this format. But I prefer to talk about it later on. So this is example. Yeah. Now let's move to something very important when we talk about deep neural networks. We need to get training data. And that's really a big issue that always people think about. I was working recently on a problem related to pavement crack detection. And in pavement crack detection, you need some data sets so you can adopt a neural network, deep neural network, or CNN, convolution neural network, in order to, get the classification, be able to build a model to classify the data. This massive data set is available for free, and you can actually find it here on. You search for CNN using MATLAB. Okay, so this is convolution neural network with MATLAB. You have some resources here, and this one, create a simple deep neural network for classification. This is actually a nice example. I would like to ask you to try it and look at it. It's very, very nice example here. If you just you just go here to view this command, and then you copy this link, and then you go to MATLAB. Let me show you how this works. Okay, and then you paste this here. You will have the the file open here. As I said before, you can save this file. You can save it as an M file, but remember, you cannot save it on MATLAB. Save it on desktop. That will be better. And also change the file name. That will be better. And then you can run this code simply like this. So actually here the system tells you, like, we have like these are the classes that we have from 0 to 9, and the number of images used are 1000, and these images are of size 28 times 28. So these are the training data that we are adopting. This is our samples of the training data that we are adopting. See, but as you can see, the resolution is not very good, but that's just the case. And now this is when the deep neural network run in order to do classification. Okay, and then it finish, and then it gets you the accuracy, which was 0.99. It's like 100% recognition. So this is very nice example. I think if you go and look at the details of this example, or even this function, and try to run it step by step, here you are defining the architecture of the neural network and so on. I will talk about this later on, but just to show you the simplicity of the problem and so on. Okay? So this is the MENSET dataset is one of the nice examples that you can try, and it doesn't really take that much time in training. So you have the input here, which is the image of the handwritten characters, and then it goes to number of deep neural network layers. Here we call something convolution, max pooling, convolution, max pooling, fully connected, and so on. So I will talk, of course, about each one of this, and this is a demo for the MENSET. You can try. Now, there are some limitation, of course, for the deep neural network is the high cost, because you know, each neuron can be considered as a logistic regression, so it's a classification problems and so on. So, I mean, these are some of the limitations. But now let's go to the deep neural network architecture, how it works, how things are done here, and I hope this will be very useful for you. So, hello everyone, welcome back to the deep learning neural network section. I already talked about the machine learning. We talked about the machine learning. If you remember, we described the difference between machine learning and deep learning, and this is maybe like one slide that talks about this. So we said the difference between deep learning and machine learning is the concatenation of the two phases, which is feature extraction and classification. So we have this as one in the deep learning. So now we need to know how deep learning work and what are these layers and their architecture. We also talked about neural network. We mentioned how the neural networks update its weight, such as that it can provide a learning process or a map between the input and output. Now for deep learning, okay, one of the very famous architecture in deep learning is something called convolution neural network. So what is a convolution neural network? It's one of the most popular algorithms for deep learning with images and videos. Like other neural networks, CNN is composed of an input layer, an output layer, and many hidden layers. So we said deep means we have many hidden layers. So that's the meaning of a deep. Feature detection layer, which is, you remember we said before when we use machine learning, so we try to segment the image, extract the objects, extract features from different objects, and then feed it to a neural network. And here we actually the deep learning consists of a neural network at the end. The last layer is a feed-forward neural network that we talked about. So these layers perform one of the three types of operation. There are three types of very famous operation, which is convolution, pooling, and rectifying. Okay. So this is two different architecture of a neural network. So if you look here on the top, so here we have the input data, which is in this case an image, and then it goes through a number of operations. The first one is called convolution. Okay, in this convolution layer, we actually extract something we call a feature map, and for the record, feature map is actually a set of images. In this case, with a little bit different size from the original image, and then we take this feature map and feed it one more time to another convolution layer, and then generate another feature map, and then we take this feature map and feed it to a fully connected neural network. So the fully connected neural network, or multi-layer perceptron, that we learned about before is actually the last stage here in the deep neural network. Okay, here is another way of representing it. We have convolution, and we have something called pooling. We will define what is pooling. We have convolution, pooling, and then fully connected network, and then we get that. Of course, we will define each one and how it works. I just want you first of all to know that this is a general architecture, so you can have many convolution and many pooling layer before you go to the fully connected layer. Okay. Okay, so we say convolution. What's happening in the convolution layer? So convolution puts the input images through a set of convolution filters. Okay, again, so we come back again to filters. So it means we have filters here. Remember, in segmentation we have filter, in enhancement we have filters. So the filters basically are a filter of different sizes. We process the image with these filters, each of which activates certain features from the image. That's a nice definition here. So each filter can extract some feature or activate some features from the image. So when you use, for example, a low pass filter, it's different from a high pass filter, it's different from a Gaussian filter, it's different from a logarithmic filter. So each filter can extract some of the characteristics. So before, when we were doing image processing, we used to try this one, try this one, try this one, and until we reach some conclusion that this one is best. Now, with a convolution layer, we can select different types of filters, apply them for on the input images, and extract the features that we need. So some of the filter can extract edges, some of the filter can extract color, some of the filter can extract specific objects, and so on. And that's what's happening when you do convolution. Then we have something called Boolean layer. So the Boolean layer simplifies the output by performing something called nonlinear downsampling. So what does this mean? It means when you deal with an image in the input layer, it will have size n times n, and we count on the Boolean layer to reduce this size as a function of time. Why? Because basically we would like to go to the smallest element in the image. The smallest element in the image is going to be the the image which has the feature that we are using, right? Just to make sure that the video is working. Okay, so Boolean simplifies the output by performing nonlinear downsampling, reducing the number of parameters that the network needs to learn about. And what do we mean by the number of parameters? It's the number of weights for the neural network. Because when you have, let's say, an input layer that deals with an image of size n times n, so it means you have n squared number of weights at the input layer. So we would like to go down and reduce this number, the n squared, as we go until we reach the multi-layer perceptron at the end with the minimum number of features or parameters or weights in this case, such as that we can feed it to the multi-layer perceptron. The other part of the architecture of the CNN is something called rectified linear unit. Rectified linear unit, or ReLU, allows for faster and more effective training by mapping negative values to zero and maintaining positive value. What does this mean? Remember when we talked about the sigmoid function? So the sigmoid function was basically a function that equal to 1 divided by 1 plus e to the minus z. So the rectifier unit is actually another function. We will see how it looks like as an architecture. So this function will map all negative value to zero, and all positive values we will keep it. These three operations are repeated over tens or maybe hundreds of layers, with each layer learned to detect different features. All right. Convolution layer is a layer which takes input and represents it in a different way, utilizing a number of filters. And the filters here are called kernels. We called it kernels. Okay, remember we said the filter is like a window or mask, or so the definition here or the naming here is called kernels. And filters are especially iterators that stride through the input and present it as a new, smaller, partially merged output. In CNN models, there are often many more than 3 convolution kernel layers. 3 convolution kernels with and 16 kernels, or maybe 64 kernels. So you could have like 3 layers. Each layer could have like 16 or up to 64 kernels, which is really a big number of to process the image. So this means that, for example, you have 16 filters, okay, that is processing the input image, okay, and now you could have like thousands of input images. So these filters should generate thousands and thousands of images in after it passes by the convolution layer, of course with a smaller size. Each filter will produce something called feature map. Why we call it feature map? Because it's not just one feature or one array of values, it's a map actually, which has number of images. The output of the layer is the stacking of all these features map. So it's many features. Typically, a ReLU activation function will follow by applied to the output of each filter. Of course, before the ReLU, we're going to have the pooling layer. Parameter of these filters will be learned using backpropagation, which is the same learning algorithm that we use for multi-layer perceptron. So convolution layer filters work on every part of the image. Therefore, they are searching for the same feature everywhere in the image. Okay, so that by the same philosophy, we get like number of kernels, and these kernels move over the image and generate new images. And these new images concatenated one after the other and is called feature maps. Okay. Here, maybe one would say, what do you mean by drop out? Drop out is actually done by pooling. We will talk about pooling. So convolution layer, as you can see here, this image. Actually, here is a low-level feature map. It can be generated from, for example, from the first convolution layer. This is maybe the second or third convolution, so we call it mid-level features, and then the high-level feature, as you can see. So the goal here was to recognize faces. So this seems like one of the application. So here you see it detects edges. Here it detects objects like eyes and mouses and noses and so on. And then after that, it can recognize the whole face. This is what's happening as an output from each convolution layer. So this is very strong idea. So the convolution function in deep learning is something like this. So you can have the image, if this is the image, and this is the filter or the mask or the kernel, and then it produces the output. How this output is produced? The output is basically, again, it's you take this mask or kernel and pass it over the image. Okay, and so you have it here, then you move one step, then you move another step down, and then another step down. So in this case, you have 3 times 3, so you will generate 2 times 2. So O11 will be what? Will be F11 times X11 plus F12 times X12 plus F21 times X21 plus F22 times X22. That's the way it works. Okay, which is same idea as we did before. This is again an example, as you can see. So this is a number example, and this is on the right is a simulation actually that tells you how it works. All right. So here we have a filter of 3 times 3 matrix. The filter is sliding through the input. All at each iteration it is doing element-wise multiplication and addition, and that will generate just one feature map, or one image of the feature map, because the feature map is created from different filters with the image, right? So sample convolution operation, here again it's a sample convolution operation. As you can see, if we have like a bigger matrix which represents the image 5 times 5, and then we have this 3 times 3, so we're gonna get in this case a feature map of 3 times 3. Okay, so as you can see, applying a 3 times 3 filter on a 5 times 5 image will produce a 3 times 3 feature map. All right, so that's something as you can see, it goes down. The number, the image size or the feature map size is going down, shrinking. Yes. Here when we have 6 times 6, so what happened? So 6 times 6, we get like 3 with a kernel of 3 times 3, you get us 4 times 4. So it seems that there is like a drop down here of the size of the images, right? So the feature map is the output of one filter applied by convolution to the input. A given filter is sliding across the entire image or entire previous layer, and it produces the feature map. If we look at one example here, if we assume that we have a kernel of this format, as you can see, this kernel is having 1 1 1 0 0 0 minus 1. This is like a differentiation, right? It's like f of x minus it's like f of x plus 1 minus f of x minus 1, something like that, because we have a 0 in the middle. Okay, so the feature map, as you can see, if this is the original image is having tens on all these columns and then zeros, so that's why it looks like something like this. Actually, it should be like white and dark. And then when we do the kernel, what happened is we get these values, so it become like brighter in the middle and black on the right. So this shows the edge. Okay, so this is one of the very successful filter. It looks like a robot filter. So it's the same story is happening. Now, if we look at another example, we have here all tens, and we have tens here, and then we have zeros here and here. So it's like 6 by 6. And then if we use the same filter but transposed, so 1 1 1 minus 1 minus 1 minus 1, so we get something like this. So this is a feature map. So it gets you the difference here between these two. Okay, so every single feature every single kernel can produce some new features. But which filter should we use? Parameter of this filter will be learned as weights with the backpropagation. So we really don't know the best types of filters in this case. So this is a Sobel operator. So you see the Sobel is one of the strongest operator that we can use. So why not use multiple filter? Yeah, so can we use multiple filter? Yeah, it's a good idea to use multiple filter because each filter will produce something, extract some features from the image and really can produce some, more results that really can be helpful or significant somehow. Of course, not all filter will produce equal important result, but again, there is a good chance that this happens. Now, one would say, okay, you were talking about like the image size and the convolution layer, and then you talk about the feature map. If we look here, there is an equation actually that represents the size of the feature map, and that's what we mention as a drop down. Now, if we have an image like this of size 28 times 28, it is fed while you are using a filter of size 5 times 5. And then you would like to get the feature map. So how this can happen? So basically you say Ni. So Ni is the size of the image, which is 28, plus 2b, where b is called a padding size. Okay, remember when we talked about the image, when we do filtering, usually the image size goes down. So the padding is like a frame we add around the picture, okay, of zeros, such as that we can produce an image with the same size. Remember that? We talked about this little bit. So assume now the padding is 0. Assume the padding is 0. So assume we don't have padding. Minus k, where k is the kernel size. So the kernel size here is 5. So we say 28 plus 0 minus 5, dividing by s, where s is a stride. I will mention what stride mean. Assuming the stride is 1, so this will be 28 plus 0 minus 5 divided by 1 plus 1. This will give me 24. And that's going to be the output of the first convolution layer, which is a feature map, will be 24. As you can see, 28 times 28 became 24 times 24. And we will talk about how we get it to 12 times 12, okay, in just a minute. So this is the equation that governs the size of the feature map after it passes by the convolution layer. All right. Okay. So this is again an example showing how this happened. Okay. This is a convolution layer here again. So this is size 23 times 23. So the feature map will be 23 plus 2 times b. We assume the padding is 0 minus 5, which is the size of the kernel. Then divided by 1, so this will give us 28 times 28 feature map. And then we have 14 times 14. I will tell you how we go down to this number using max pooling. Okay. Now, what is padding? Padding, as I said before, it's when you have the original image, like this is the original image. You see, 0, 1, 2, 3, 4, 5, 6, 7, 8. If this is the original image, and this is the filter that we're gonna use. If this is 3 times 3 and this is 2 times 2, then the output will be 2 times 2. But if we added padding, if we add padding around the image, like another, layer of zeros around the image, what's going to happen? We will be able to produce again 1, 2, 3, 4, 1, 2, 3, 4. This is going to be 4 times 4. So this is the data here is 3 times 3. So we add 2 padding here. So this becomes 4 times 4. So we are not losing actually information. But what is on the border here is going to be like, extra data that might not be significant. So it should be like 2 times 2, but the padding actually is on the side, but it doesn't really mean a lot, because as you can see, the values are very small in this case, which can be like appearing like as dark or black because of the padding here. Stride. What is a stride? We said in previous example we default to sliding 1 pixel at a time. What we do is we take this kernel, and then we pass it by this one, then we pass it by so we start here. Let me try to show you what stride mean. So for example, we pass the filter on this boundary, okay, and then we move 1 step, okay, and then we move the next step, and so on. So always we move like 1 step at a time, right? And that's why we call stride as 1. But if we move 2 steps, like we start here, let me try to change the color here, ink color. Okay, if we start here, okay, and then we moved immediately to the next one here, so we say we have a stride of 2. So the stride of 2 can reduce a little bit the size of the image that we are trying to do. Okay, that's what stride means. So when computing the cross correlation, we start with the convolution window at the top left corner of the input array, and then slide it over all locations, both down and to the right. In previous example, we default to sliding 1 pixel at a time. However, sometimes either for computational efficiency or because we wish to downsample, we move our window more than 1 pixel at a time, skipping the intermediate location. That's the basic idea of stride. So padding increase the boundary of the image by zeros, and stride is, instead of moving 1 step of the sliding window, we can move 2 steps or 3 steps, and that's what we call stride as S. Now, the next step is max pooling. In max pooling, after we get the feature map, what we do, after we get the feature map, we do some kind of max pooling or maybe min pooling. So what we do is, after we get the feature map, we decompose this to number of windows, and then we pick up the maximum value in each window. So the maximum value here is 6, 6 will be here. And then we check the maximum value here is 8, so 8 will be here. And this definitely, what it's going to do, it's going to drop the size like this. So the size of, you remember, if we look back here, okay, here for example, so the size here was 28 times 28, and then when we did feature map by max pooling, so we got it to 14 times 14. And I think here also in one of these images, I hope it's right. No, it's not this one. So this is 14 times 14. Yeah, and there was another one which is 12 times 12. Yeah, I remember. Okay, so here also this is another way of doing pooling. So we have max pooling, and then we have average pooling, and we could have min pooling. So max pooling is basically you pick up the maximum value in this square, and here you pick up the maximum value, so it's 30. You pick up the maximum value, which is 112. You pick up the maximum value, which is 37. Or you can take the average pooling. So the average pooling will be 12 plus 20. So 12 plus 8 is 20, plus 20 is 40. 40, so it's 40 plus, so it's 52. So we get like something like in the middle, like 13. So we try to approximate it. And so on here, it's 32. So it should be, we divide by 4 actually. We divide by 4. The average is divide by 4, not divide by 2. So this is 32 divided by 4, so it gets us 8, right? And so on. So that's the way the max pooling and the average pooling works. Okay, so it's a kind of approximation of the image. So for the drop down, randomly we can drop some unit along with their connection during training. It helps to learn more robust features by reducing complex co-adaptation of the unit. So sometimes we can drop some units. There is of course a mechanism on doing that. So we do not want our network actually to get overestimating the result. Then at the end we have this fully connected layer. Here at the end we have the fully connected layer that we know about, or that we talked about before in the neural. So basically here we have the features. All the features are fed here to the fully connected network. That's the idea. And so of course the size here is going to be very high or very larger than the size of here, but of course we end up with a multi-layer perceptron or fully connected network to recognize. And then the output, the number of output actually depends on the number of classes that we are dealing with. For example, dog, cat, boat, bird, or any object that we are handling. Okay, let's check the size of the recording. Okay, and then after that we have the rectifying ReLU. So the ReLU is actually a function which has zeros at the end or at the negative side, and then 1 or linear curve at the positive side. So for example, we see 0.77 is still 0.77, and any negative value like here, so any negative value like here, like this one, minus 0.11 is here 0, and 0.11 stay as it is, and so on. So any negative value like here becomes 0, so we get rid of the negative value from the feature map. So it was found that this function is working very nice in cases like this, so you get rid of the negative value. So the convolution layer, again, when you use, now you can have, of course, if you talk about color image, so you can have a size 3 times 3 times 3 filter, and then you get the output feature map and so on. You can create the volume of feature map. All right. So here, this is another example. Let me try to do this here, so it looks nicer when I upload this. Okay, so when you have an image of size 32 times 32, then the feature map after the convolution layer becomes 28 times 28, and then after the second convolution layer it goes down and goes down and goes down. Okay, so there is some problem if we shrink the image size quickly, that sometimes is not good and it might not work. So we need to make sure that we select the size of the kernels appropriately. So some people use some large kernel at the beginning and then a small kernel at the end. So this makes the shrinking not too fast. So you can extract really the good feature of the image. So this is again the description of the convolution layer. So it's in between the convolution 2D layer and the dense layer, there is a flattened layer. Sometimes we have a flattened layer. It concatenates all the feature map into a single long vector to feed to the dense layer, which is feed forward. Dense is the layer type we will use for our final calculation and output. So that's what we do. So we can concatenate all the feature map, so it becomes like input to the here. Look at this. It's the flattened layer here. So this is what we do at the end. Okay, at the end here, the flatten layer is actually take all the feature map and make it as vector here. All right. So that's the mechanism of deep neural network that I want you to learn about, so you can understand how the flow of data or the flow of information works. So we can have, in some cases, with some complex problem, we might have like maybe 10, 20, 30 layers of convolution layer, and that's why the processing of this type of deep neural network takes some considerable amount of time. Of course, some examples are easy to do, like the example of Mensa data set, which is digital, the handwritten digits. It's very nice and easy. When we train the neural network, there is some type of data we need to collect always, which is accuracy and loss. So the accuracy is always something like this goes up, okay, and you try to approximate to like 100% accuracy. It means, well, let's say when you enter 100 image, you get like maybe 90% or 95% accuracy, maybe more. It depends on the structure. And again, the structure of deep neural network is actually it's not an easy problem. It's a complex optimization problem. What is the best structure? So I had one of my students was working on some case study related to plant disease detection, and we try to explore different types of architecture of the deep neural network. We also try to explore different resolution of the image. So what happened is we figured out, our finding was like, yes, you can have better resolution. The more resolution you have is the better, but there is some resolution which is really in the middle, and that can save you computation, and it can provide some nice nice results, again acceptable results. So it's not always the case when you increase the number of layers. Too many layers will get you good results, but also with acceptable number of layers and high resolution image, you might get good results. So will CNN solve all of our problem? That's a good question actually, but I mean, like, there is currently tremendous application that adopts convolution neural network with wonderful results. I mean, here there is some mistakes on defining, okay, this is a dog. If something like this happens, so it means maybe that there is some overlapping between the features of the different classes. That could be the case, or you don't have like adequate number of training sample, or you might not have are not using the best architecture in your case. So you might need to revise your experiments and solve the above problem. So deep neural network software, there is lots of tools. Many people use TensorFlow and Caffe, okay, and PyTorch is also some of the techniques. And as I said, MATLAB is one of the good technique. This is, by the way, a code on Python if you would like to utilize it or use it on Python, but you need to include the appropriate library to run this code. And if you look at this link, you will find all the information. And also, if you look at GitHub, in GitHub you find lots of resources for that. And this is for menaced classification using CNN. This is the code for doing, this is with TensorFlow. You can do it. And as I said, you can, if you go online, like with MATLAB, if you go with CNN with MATLAB, I think maybe I said that in a previous recording. So if you go here, there are some information about that. Here you create a simple deep neural network for classification. If you click here, so this is an example that you can utilize to solve that. Here it shows that the input layer, so you have the size of the input image. This is a grayscale image of size 28 times 28, because this is 1. So this one means you're having a grayscale image. And then you have a convolution layer, then batch normalization layer, then ReLU layer, and then you have max pooling layer. Of course, if you go and do help on max pooling layer, you will see what's happening. So this is a stride. So you have a stride of 2, so means you jump or ignore or move the window like 2 steps at a time, and then the stride size is 2 times 2, and so on. And as you can see here, you have a fully connected layer at the end with neurons, 10 neurons. Why 10 neurons? Because here we are trying to recognize like 10 digits, 0 up to 9. That's why this is 10. I think it will be nice if you can, explore this. And this is the options that you can have. So we have initial learning rate. You can play with this initial learning rate, and actually it will affect the speed of conversion. The maximum number of epochs is 4. Okay, and IMDS validation is the validation data. Okay, so at the beginning we do that, and this is a conversion curve. As you can see, this is accuracy. So it almost reached like 100%. So it means accurate classification of all the training data. And this is the loss. It means the error goes down as a function of time, reaching up to 0. And then after that, you do the classification here. This is a very powerful, technique. So here we can say view command, and then you can take this command, copy it, and paste it on MATLAB. Then you will find this whole program in MATLAB. All right. I think we covered the most important part of the deep neural network. The only thing is left is I want you to try to explore MATLAB with this code and see how it works, and definitely you will feel more than happy. By the way, there are benchmark cases where there are something called Alexnet. Alexnet is one of the very famous network, and VGGNet is also famous, and ResNet. By the way, this is a trained network that exists, already trained, but it was trained actually for some, a different application. There is something in deep learning called transfer learning. So you can utilize some of these networks actually and retrain them to do some kind of application that you select or for yourself. But transfer learning actually is a whole different field, and we might not be able to cover all of it, but I just want you to know about it. If you have a pre-trained network, you can download. There's also GoogleNet. You can download that networks and do some kind of changing for the multi-layer perceptron layers architecture, and then train the network one more time, and then you can get your results as quickly as possible. All right. Thank you so much for listening, and I hope you can utilize some time for doing deep learning, so that in our lecture on Friday we can check and see some of the examples. Thank you so much, and best.